So now that we've demystified GC control and GC hardware, the link to those videos down in the description. Now it's time to demystify GC method development. So let's go to the GC and demystify. Method development is supposed to be the most complicated thing in our field because it means coming up with a recipe. Most people look at a GC recipe and they probably try and figure out how would you come up with those conditions, because we have to choose the right column length, diameter, film thickness, stationary phase, temperature program. But of all those things, it turns out that the temperature program is probably the most powerful. So another way to put it, whatever column you have in the GC right now is a pretty good starting point, because no matter what kind of column it is, it has a boiling point separation built into it, right? All GCs do. So let's start with whatever column we have. Right now, I'm using my favorite column. It's a 0.25, 30 meter DB5. So, and when I say DB5, it could be RTX5 or ZB5 or whichever brand you're using. But the 5 column is our sort of our go-to column when it comes to method development, or you're going to find that it's going to do most of the separations that are out there. So let's go ahead and set up the GC. I'm going to teach you how to listen to your sample. So we're going to have to find this temperature set of conditions. We need to find out what temperature we start at, what temperature we end up with, how quickly we go from initial to final. And those sound like they're complicated questions, but the sample will tell you the answer to them. So what we're going to do is we're going to try the entire universe of temperatures. What I mean by that is that in GC, the lowest temperature we can use on a GC is room temperature. So I have my GC set at 40 degrees. The highest temperature is dictated by the column, and for mine, the max temperature I'm setting is 300. So you would typically go from room temperature to column max, and that's the entire universe of temperatures. Now we can extend that universe a little bit. We can go up to, instead of 350 for a regular column, we could go up to maybe 420. If you have a high temperature column, up to 450 technically. If you want to go below 40 degrees, we can get cryogenics on our GC. We could go down to -70. So we can extend that, but most of us are going to work in this range, 40 to 300. This is going to accomplish most of the tasks when it comes to developing a method from scratch. So let me take you on a tour of the GC itself from the software perspective, because in the software is where we're going to set all of our parameters. So in this case, I'm running an Agilent 7890A. The software I'm using is B.0403, if anyone is really interested in what it is. But every software out there is going to have these same parameters in them. And that is the ability to adjust things like the auto sampler. So the auto sampler, think of it as it's a robot, and it's going to inject things for us. So the most important thing is we set the volume. We're going to inject 1 microliter. That's what we're typically going to inject. So when we do method development, let's just keep things simple. I usually like to do 1 sample wash and 2 sample pumps. It just is telling the syringe how many times to pull back the plunger. In real life, I would do a solvent wash post injection. So in real life, I would turn that on, because after the injection, I would do a wash. In this case, I'm just doing 1 injection for demonstration. So I'll leave that on, but we don't really need that. The next parameter that we can look at is valves. Now, most GCs do not have valves. If you're doing permanent gases, then you're usually going to have a valve installed. You could have up to 2 valves installed from the factory, and this is just allows us to make an injection of a gas sample instead of a liquid sample. The inlets. So typically we're going to set it 250 degrees is my favorite injection port temperature. That's going to work for most samples. If you know your analytes boil at high temperature, if we're doing some forensics work and we know that the benzodiazepines boil at 300 degrees, well then I'll set my injection port to 300. But 250 is usually the right answer. We always start in the split mode. Split ratio, where do we start? I don't know, 100 to 1, 50 to 1 are 2 really good starting places. What that's going to do is it's going to dilute our sample 100-fold as it injects it onto the column. That's a pretty good number. If we want our peaks to be bigger, we'll use a lower split ratio, 50 to 1, 25 to 1, 10 to 1. If our peaks are too big, we'll then go to a higher split ratio. Instead of 100 to 1, 200, 300 to 1. So we're going to use that. I call that our sensitivity adjustment. We're going to adjust the sensitivity just based on our split ratio. So we'll start with 100 to 1, so we can see what the first run looks like. Next one is the columns. The GC needs to know what your column is, more so from a physical perspective. It needs to know the column length, diameter, and film thickness in order to set the pressures and flows properly. So first thing I notice is this is not the correct column. So this is a 0.18 millimeter ID column. It's not the one we're using for this particular sample. Right now, our column is a 30 meter 0.25. So we're going to change the column. And to do that, we're going to click on the little thing that says change column. And we're going to go into our inventory and we're going to replace it with something. And lo and behold, my inventory is empty. So I haven't added anything to this computer yet. So let's add a column to the inventory. And how do we do that? Well, you click the button. It's going to give us a list of a bunch of Agilent and J&W columns because it's their software. You could type in your own column information. You could type in your own column dimensions. But since we're using an Agilent column, we'll pop in and take a look at it. It has a part number on it. They all start with 19091J433. So 19091, and we're going to scroll down till we have J433, right? J433. Oops, right there. 19091J433, and that says, oh yeah, that temperature max is 325 degrees. It's 30 meter, 0.25. So it has all that information already because it knows what the column is. I'm going to say add, select the column to inventory. So now that I have that, when I say install select column, it's going to come in here and say, oh yeah, I now realize that your column is a 30 meter 0.25. It's going to adjust the pressures and the flows correspondingly. The other thing we'd like to look at is the flow rate itself. We always like to run constant flow. So here's the choice, constant flow, constant pressure. It's a beautiful theoretical discussion, but the easy answer is constant flow will always give you better results, or a better way to put it. You'll either get the same results or they'll be better when you're using constant flow. And we typically start at a linear velocity of 32 centimeters per second. It's a good starting point. It's pretty close to the optimum. It's probably not going to be our final number. We're probably going to up that at the end to get better separation, or I'm sorry, to get a faster analysis. But for right now, we're sort of stacking the deck in our favor. We want to see the best separation possible. The other thing I noticed while looking at this is it says front inlet is using hydrogen. And it turns out that, yes, we're using hydrogen as a carrier gas on this instrument, which is why the pressures are generally so low. You don't need a whole lot of pressure with hydrogen because it's not as viscous as helium. So this thing is running 6.6 psi. It's running 1.1 mil per minute. But what I typed in, the thing that highlighted in blue, I just typed in linear velocity 32 centimeters per second. Okay, so that part, I'm going to hit apply just to make sure everything there stays happy. We go over to the oven. So the oven, we really don't know what to expect. So we are going to use this formula that I've used for every method development project I've done in the last 30 years, and that is room temperature, 40 degrees, hold time, 0 hold time. Let's keep this simple. If you're doing splitless, then the splitless time, the hold time will be the same, but we're not doing splitless. The ramp, I like a 20 degree per minute ramp. It's a decently, a decent rate. The slower the rate, the better the resolution, but it takes longer. Faster the rate, the faster the analysis, but the resolution is not as good. So let's start at a decently fast clip of 20 and see what it looks like. The final temperature of this column technically is 325 degrees, so we'll type that in. And I always like to put a hold in at the end because if this is a real unknown, we don't know how many peaks to expect, so let's make sure we wait long enough to all the peaks to come off the column. Column max, another 5 minutes. That way we're sure that everything has come off. Okay, so that's my oven conditions. Detector, usually nothing too exciting here. This is running my makeup gas, which is, I like to run constant column plus makeup at 30 mils per minute, and then running 40 and 400 in terms of hydrogen air. These are typical numbers that will set once and never change. The only time you'd ever change your detector temperature would be if you're doing high temperature work. So if I really were going up to 420 degrees, I would up that detector temperature. In this case, I know I said I'm going up to 325. You know, my gut feeling says I'm fine at 250. It's probably not a bad idea to up that to 300, but I'm not going to do that right now because I know that 250 is going to be fine. So those are all the conditions. Those are all the parameters we could set on a GC. Now, most of those we're going to leave alone, right? We've installed the column, so we don't have to do that again. We're going to use 250 injection port temperature, 250 detector temperature all the time. The only thing you're really going to change is flow rates and temperature. Those are the common things that we're really going to get the most bang for our buck when we're doing method development. Okay, the other things in here, events, I don't know, we could set up timed events, signals. What do I do if I'm, typically we can have up to 2 detectors on the GC, the front signal and the back signal, and we can assign them differently. So in real life, we would always assign the front signal to the FID, the front FID, and then the other one would typically be the back FID. In this case, we're using it as we're setting the oven temperature to the back signal. Configuration, if we were messing around with hydrogen versus helium, we'd come up in here and say, oh, I'm using hydrogen as my carrier gas. This is where we would change from hydrogen to helium to nitrogen to argon methane. These are the counters. In real life, they're nice because you can count the number of times we've made injections over the septum. And then this is just what the GC is going to look for in its readiness state. So most of that stuff we're never going to touch. We're going to just come in here and tell it our oven temperature, temperature program, and then we're going to go in the column and tell it our linear velocity, our flow rate. So now the GC is ready to go. I have a sample. This is we call it a GC unknown. There are 10 compounds in the sample, solvent plus 10. So you're going to see a little bit of a solvent cluster, and then we should see the 10 compounds come off. So let's go ahead and start this thing. I'm going to go ahead and just give it my initials, and then come up here and say we're going to go 40 to 325 at 20 degrees per minute. So that's sort of the first set of conditions. I'm going to say run method. So now what's going to happen is the GC's got to get in the ready state. It's waiting for prep run. If you can see that on the screen, it's waiting for the prep run. That means right now we have the gas saver on. The split flow is set very low just so we don't waste stuff. And right before it makes an injection, we're going to see it up that flow. So here it's taking our sample. It's going to draw a full syringe. It's going to throw it away. That was sample wash. So now it's going to go into the sample, and it's going to pump it twice to get rid of the air bubbles. And now it's going to set the flows properly. It's going to wait for the split flow to come up to what it should be, and then it'll get its ready signal and make it the injection. So the injection's been made. We can see that the time starts at 0, so it's resets the clock. And as we see the chromatogram progress, we will see both the retention times of the peaks, and we also see the temperature running on the red line on the temperature programming line. So I will let that proceed. So let's take a look at the chromatogram. It's still going, but we could count and see that our 10 peaks have come off. And a couple things we're going to notice. First, our solvent front is there a front. These are hexanes, so it's different isomers of hexane, all sort of co-eluting. If you wanted to separate that, then we would have to start at a lower temperature. So instead of 40, we'd have to go down to 30 degrees. In that case, if we really wanted to go after those, I would go to a thicker film as well. But those are not our compounds of interest. We're out here. We have a bunch of hydrocarbons. I've got 2 alcohols. So the one thing that jumps out to me is, although we see beautiful separation with the hydrocarbons, look at the peak shapes of the alcohols. Let me zoom out for a second. Can you tell which ones they are? See, beautiful, symmetrical, tail, symmetrical, tail, symmetrical, symmetrical. So those 2 tailings, tailing is caused by 2 things. Either a bad column installation or adsorption. Something is sticking to something dirty. So what kind of things stick? Active compounds, acids, bases, and alcohols. Ding, ding, ding. Those are alcohols. They're sticking to some dirt. I know this is a great column installation. How do I know that? Well, take a look at the other peaks. You see the beautiful peak shapes? That says I must have installed the column properly. The fact that this guy's tailing must not be a physical problem because they'd all be tailing. This has to be what I'd call a chemical problem. Chances are there's a little bit of dirt in the liner or graphite, a little piece of graphite has fallen in there, and that would cause the tailing peaks. So that's real life. I didn't plan that to happen, but welcome to my lab. Welcome. This is Lee on a Friday afternoon. So we could stop the run. So I'm going to go up here and say stop run. When I stop it, it's going to integrate the peaks and then give me a printout. And then on the printout, I could take a look at the numbers. So the numbers that we care about things like our capacity factor is a good number. We like the fact that our resolutions are good. So the bottom line, what we really care about here, and keep in mind these first couple of peaks are the solvent front. They don't really count, right? We don't care about those guys. But all of our peaks of interest, I believe, probably starting right here, 3.075. Oh yeah, you see the numbers. That guy right there looks like it has a resolution of 12, 37, 35, 38, and 7.5 are the worst resolutions. Remember, resolution needs to be at least 1.5. So in this case, we have too much resolution. I know that seems like a good problem to have. In real life, if you follow this approach and do room temperature to column max at a slow rate, like 20 degrees a minute, chances are you're going to get a good separation. Why is that? Well, you stack the deck in your favor. We got over 100,000 plates on my column. I'm doing a slow program on a good column. Generally, it's going to lead to good separations. So if you have too much resolution, let's address this problem. Let's use a much higher temperature program. So this case, let's go in here and instead of, so we're going to do two things. We're going to start at a higher temperature, and I'll show you how we figure that out. There's a little cursor that is following along. We care about the very first peak, and that very first peak is coming off, coming off at a temperature of, can you see it? You look at the bottom left of the screen, that first peak is coming off at a temperature, oops, I think we've shifted here, sorry guys. First peak is coming off at a temperature of about 100 degrees, which means our initial temperature could start at 100, and our final temperature looks like it's not going to really have to go up too much above 190. But let's do this. Let's go to the oven, and let's set the initial temperature to 100. I'm going to hit apply, so it'll start moving up there. And so we know we need to start at a higher temperature. The programming rate, if I go to a higher rate, we're going to go to lower resolutions. So I always tell people double it, see what happens. So we're going to go from 20 to 40. I'm going to make life a little more fun here. I'm going to go from 20, I'm going to skip 40. I'm going to go all the way up to 80 degrees per minute. That is a very fast programming rate. But what we're going to see is that will decrease some of our resolution. Actually, should decrease it a decent amount. By doing this, we're going to take this long chromatogram and squeeze it to a shorter chromatogram. We're starting at a higher initial temperature, so the first peak will be closer to T0. And then we're using the higher rate, which will squeeze the peaks closer together. So let's go ahead and try this set of conditions. And I guess we should tell it the information. And we're going from 100 to 325 at 80 degrees per minute. So as we run this method, we should first of all see the same sort of auto sampler doing its thing. It's going to rinse once with the sample, throw it away. It's going to then go back to the sample. It's going to pump twice and then make the injection. Remember, it's got to get ready. Make sure the split flow is ready. So let's see what 80 degrees per minute looks like. There's a chance that those peak shapes clean up too. I'm just saying this off camera. This doesn't have to be part of it. Or it could be part of it.
Why would they clean up?
Yeah, so I'm hoping the peaks might be better looking this time. And why would that happen? Well, if there's something in there that's some active sites, imagine it's like Velcro, and it's sitting there and it's trying to stick onto my alcohol. If somehow the first time through I passivated it, I sort of covered up that Velcro with the first couple of alcohols, that maybe the next injection will be better. It's a crazy concept. It's sometimes called a loading dose, and there are examples in chromatography where it really works. More embarrassing than anything else, but it's in ion chromatography. It's not unusual to inject a huge concentration of like chloride first to just shock the column or sort of fill up all the active sites. Nah, still have a tail.
I wonder if we got baseline separation between the alcohol and
It will, the resolution will be fine,
Okay.
because resolution is calculated based on the peak width and half height, and it assumes symmetry down to the base.
Okay.
So we could blow it up. So there's 2 more peaks. And this is an example. I need to remind me to chat with Ruth. Like, I would not want to run the sample in the class because those alcohols are way too small. They should be bigger. I mean, the fact they're tailing is part of it, but the area counts are low, which this, I think, came from a dilution from the thing was in the freezer. The alcohols were precipitated out. Someone diluted it and didn't get the alcohols.
Why do you want them bigger though? 'Cause
Oh.
sometimes in real life you run into this situation where
Yeah.
some peaks are bigger than others.
Yeah, actually, you're right. Right. Oh, sorry. I want to change that. So that's the last peak. Okay. So the camera's still rolling. So we could have. So let's evaluate this chromatogram. Clearly, it's happening much faster, right? Instead of our previous run, we're running much faster analysis, just a little over 2 minutes. If we sort of zoom in, we can see our hydrocarbons are looking great. Unfortunately, those 2 alcohols are definitely, there's definitely an issue in here somewhere inside the GC. Where is it in the GC? I will bet 99 times out of 100. It's in the inlet, it's in the liner, maybe the gold seal. It's going to be in the liner, maybe the top of the column. It's not going to be further into the GC like that than that. So let's go ahead and stop the run and see what our numbers look like. So again, we're going to look at our peaks of interest, and the first peak of interest we'll see based on the area. Yeah, so here's our first peak of interest, has an area of 200. We come over here and we look at our resolutions. So, starting with this guy, there we go. So we have resolution of 15, 18, 20, 16. So we got a 5.5 and a 5.2. So those are our lowest ones. Those are the alcohol, what I call the critical pairs. Now, you might look at the peaks and say, I don't think the separation is very good because of the tail. But remember, first of all, they are separating. If you look at the baseline, they are separated. And secondly, the calculation is based on the peak width at half height. So it's assuming symmetry down to the baseline, which is why the resolution numbers look so good. Okay, so here we took our initial run, which was, 8 or 9 minutes. And now we took it down to a 2.5 minute run. One last little trick I'll show you, and that is if you look at your chromatogram and look for the biggest empty space, because the biggest empty space is where you're going to be able to gain the most speed. So in this case, the biggest empty space is nowhere in the chromatogram. It's before the first peak. It's before T0. Now, I know what you're thinking. Well, I can't move this first peak any further in because I'm afraid the other peaks will move in. Well, this is anytime you see that the biggest space is before the T0, then it's time to increase your flow rate. So by increasing the flow rate, we're going to take this whole separation and just bring it all in faster. So let's go here and go to the column. And instead of a linear velocity of 32, oops, it bumped up a little bit. Let's go to 64, let's go to 128. How about that? Double, double. And we'll go ahead and apply. So for it to do that, it's now applying a lot more pressure, 32 psi. We'll keep the temperature program alone. We could go higher if we wanted, but the GC really can't keep up at up above 80 degrees per minute. So let's go to run control and tell it linear velocity, which is mu equals 128. And we'll do this as our one last run to see ways to not only develop a method, but to also optimize the method in terms of time. So anytime you have empty space in a chromatogram, it's an opportunity to make things faster, which means using a higher rate, instead of 20 degrees a minute, I went to 80 degrees a minute. That squeezed these peaks closer together. Starting at the higher temperature, 100 versus 40, we move the first peak closer to T0. And then by using a higher linear velocity, hopefully what you're about to see is all these peaks will shift in together. So we're just going to shorten all the retention times by going to the higher linear velocity. So I'm sorry, I'll double click on here. We're back to reality. And I'll expand it and watch the chromatogram develop. The nice thing about the high linear velocity is that the solvent comes off very quickly. So we've greatly reduced the amount of time we were waiting for the solvent. And now our peaks of interest are coming out. The other thing you'll notice is the peaks are getting taller. Why is that? Well, area is conserved. So if I take a peak that was short and fat and I make it come off earlier, it's going to be skinnier, which means it has to be taller to make up for it. And that's what we're seeing here. That looks like one of our alcohols. Now, when the chromatogram finishes, I'll zoom in on it so you could tell that I believe the separation is probably still pretty good. There's our second critical pair. And one more peak to come off. So the nice thing about this one is we're 1.5 minutes and we're done. Let me zoom in. Now, I'm not thrilled about that baseline. This can be and will be solved with once we clean up whatever is in the injection port. So the number is still going to come out good because, again, it's using peak width at half height, which is here, and this guy, so it's using this peak width. Oops, I'm sorry. It's using, this peak width compared to this peak width. So it's going to calculate a good resolution, but obviously I'm not thrilled with those little things on there. So we illustrated how to develop a method and then how to optimize it by cutting down the analysis time. Let's go ahead and stop the run, and we'll see our final numbers. And again, our worst resolution is now 3.7. So, like I said, it likes what it sees, even though we're not thrilled with it. So let me show you two more things while I'm here. If you notice on that printout, it showed some negative numbers in terms of capacity factor. So why would capacity factor ever be negative? It can't be. So it means that the column length is not what it thinks it is. What I'm getting at is I believe this column length needs to be calibrated. And I'll show you how to do that. It's a pretty cool little trick. Most people don't know this one, but if we go to our column, and you'll see a little thing here, it says calibrate column. If you don't find that button, go to change column and see if it's in there. One version of the software, they hit it inside change column, but we're going to calibrate column. And we're going to go here, if unretained holdup time is known. In other words, if we know our T0 time, then we could calculate the length of the column. So if I say calculate length, and what I'm going to do is I'm going to look at my last printout. For this to work, for this to be valid, the GC has to be under the exact same conditions that it was just run. So my T sub 0 in real life came out at 0.191 minutes. Now it said, based on everything it knows about my column, it said my T0 should have been coming off at 0.39 minutes, and we're saying, oh, no, it's coming off in about half that time, 0.19. So I'm going to type in the actual number. So notice currently it thinks the column is 30 meters long. So I'm going to type in that number, 0.191. And now it's going to tell me what the column length really is, and it's also going to have a little issue with it, but here we have a number of 20 meters. So it says, hey, your column's not 30 meters long, which it was the day that I bought it. Now it's only 21 meters long. How does it know that? Well, it knows the T0 time, it knows the linear velocity, and it does the calculation. So if I were to say okay, it will then put that in as the new column length. Unfortunately, it grays that out. It's just a little thing about the software. It won't let you cut off more than 5 meters of a column. It sort of considers the column to be that you should replace it. There are ways to go back in and force that. What you could do is you could create your own column. First you could try and set the length and just tell it 21 meters and see if it accepts that. And if we come back in here and look at the length, it's still going to have an issue. It's not going to accept us typing that number. So here's my trick. This is a major workaround, but let me go in here one more time. Length only. No, it's still set at 30 meters. So I'm going to go back in, cancel this. I'm going to change the column. Okay, bear with me here. I'm going to install a new column. And let's see if it'll let me just type it in here, 21 meters. And if I say okay, it comes back and says, yeah, Lee, now you got a 21 meter column. So if I set back to 128 centimeters per second, like it should be, and by doing this, we will have corrected those numbers. I'm going to go ahead and do one more run just for fun, just to see how this makes a difference. And I'll call this one calibrated column. And go ahead and run the method. I don't expect anything to be dramatically different, but we will at least be running under the correct conditions. And when you see the printout, we will no longer get negative numbers for capacity factor. The numbers will be more valid when we use the correct column length. Okay. So this one will actually be slightly longer because I believe the new linear velocity will be set more properly, would actually be a little lower than it was before. Another way to put it, we told it to run to 128 centimeters per second. I think it was running 148 based on the column length. So this one will clean up those numbers. Okay, so there's our separation. 1.5, 1.6 minutes. Very nice for 10 peaks. We'll go ahead and stop the run. And now, hopefully, we won't see too many of those negative capacity factors. And sure enough, our capacity factors are legitimate. Our resolutions are still fantastic, except for that issue of some kind of dirt inside the instrument, giving us that dirty liner. So what I'd like to do next is I think I'm gonna go in there and change that liner and pull it out and see what we find. So in that last video, we developed a method from scratch, we optimized the method, and then we ran into a problem. Welcome to real life. We had a problem with tailing, and it was tailing on some of the peaks. So you have a choice now. You can either watch me fix the tailing problem, I'm going to change the liner, or you go on to the next video where I do another method development project. This time I run into the classic roadblock where I try everything we typically try, nothing works, and now it's time to change the stationary phase. So the links to those videos down below in the description.